So what about if you just increase the density a little bit and stretch the region of the heavy fluid? So it's essentially make it extend to the surface. And that's the difference to the previous case that okay, so and that doesn't take long. You know what you need to do is you do these changes, and you do that with double do loop. You just change a number here, figure 29. Then you compile your model code, save, compile, run the simulation. It will take a little bit longer already because there are quite some a number of iterations. First of all, you have to solve make predictions. Every time step you have to make predictions for a two-dimensional model domain, which has 100 times 50. Okay, so that's 5,000 grid cells. And the time step, something like a second or so. So you have to do many calculations and repeated calculations. It takes a long time. Depends on your computer. It gets even worse if you have three-dimensional computer. And imagine that you can actually produce lots of. So let's have a look at these snapshot outputs. Okay, let's have a look here. Snapshot outputs. And in this example, you can actually see something like a plume head. You have one bulk plume head, the red here, moving over to the east. And in addition to that, there are some, we call them vortices, elements separating from this plume head and moving. This looks like a breaking internal wave. Now have a look at the simulation, right? So let's look. Pretty cool, doesn't it? And this is the simulation of a density-driven flow. And if you ask me, well, is that realistic? I mean, then you have to build a tank. Your tank has to be, really doesn't have to be 500 meters long, but it has to have the same proportions and the same. And then you compare film the behavior of a physical fluid of a lab experiment, and then you compare it. And then you know how good this result is here. But what you have to expect is, it is diffusive. So the diffusion is always, in these numerical models, there's always excess artificial numerical diffusion through the use of an advection scheme. That's how it is. What about we even make it a little bit more interesting? Why don't we just change the depth distribution? Just change the bathymetry. What about you do something like shown here? You actually include a little ramp, and a vertical obstacle here. You can do that too. It doesn't take very long in that model. You just again use do loops and to just specify where are your dry grid cells. You have obstacles. So the question that I ask now is, can reduced gravity plumes, different name for these different flows, can they jump? And let's have a look at the I'm not sure what comes on the next, the simulation. No, these are the snapshots, and you can see that they can actually jump. Let's have a look at the simulation. Simulation coming now. Yep. This is how it looks like. Simulation of a density-driven flow. Using the same model that we use to simulate short gravity. The only changes we included density, and we don't use the wave pedal anymore to simulate. But it's all within the same model. This same model can still be used to simulate the short surface group. Fascinating. It's all in the same equations. So there are different things, different dynamical processes that depend on type of forcing that you use as one aspect. I show you many more examples. All right.